Alright guys, welcome back. Today we're going to be talking about reaction mechanisms, and then we're going to be looking at the ozone layer depletion, since I think it's a nice sort of application of this reaction mechanism stuff. The chemical equations that you are accustomed to seeing are generally describing a net reaction and not the individual steps of a reaction. A reaction mechanism is a series of steps that starts with the initial products, proceeds via some intermediate species, and then ends at the final products. Reaction equations can be written for each step of the mechanism, and these individual steps are generally describing single collisions or simple decompositions, and these are called elementary reactions. So, an elementary reaction is just something that describes an individual collision or a simple decomposition, and these elementary steps must add up to give the original must add up. Each step must add up to give the overall equation, more or less. And each step of the reaction has its own rate, which contributes to the rate of the overall reaction. So each step happens at a particular speed, and therefore that can control the speed of the reaction. So here's an overall reaction, and then here's sort of the mechanism where we have step one, where we're told this is the slow step, and we're told that's the fast step. The thing highlighted in red, nitrogen trioxide, is what we call an intermediate, which is a species that exists as a reaction proceeds, but is not an initial reactant nor is a final product. So, an intermediate is produced and then used up. A catalyst, however, which sometimes can take place in a reaction mechanism, is generally used up and then reproduced at the end. And we'll see this sort of later on in organic when we look at the nitration of benzene, I think. Yeah, the nitration of benzene. An elementary reaction is just, again, a reaction that involves a single collision or possibly a simple single decomposition, and these mechanisms are a series of one or more elementary steps. Unlike the other reactions, you can actually write the orders, the exponents on these steps. You can write the orders with the little stoichiometric coefficients. Therefore, the orders in differential rate laws cannot be written using stoichiometric numbers for the overall reactions that aren't elementary. However, if they're elementary reactions, we can use those stoichiometric coefficients, the numbers in front of here, to fill in the orders. So, for example, we know that if we look back at our example here, this one here, we know that there's two NO2 molecules, so therefore the order for NO2 is a second order. It's second order with respect to NO2, and it would be first order with respect to. And the second step would be, it would be first order with respect to this intermediate and carbon monoxide. Molecularity is the number of species involved in the elementary reaction. Basically, the exponent here tells us how many of those molecules do you need. So, for example, the order tells us the molecularity of the species, and the molecularity gives the number of species involved in an elementary reaction. So, a second order reaction is bimolecular. A unimolecular one is a first order, and a termolecular is a third order reaction. So it involves the number of species involved in an elementary reaction. So this 2 here, actually, this isn't coincidental, and when we determine this experimentally, what we mean is that you need two NO2 particles to collide. You need two NO2 molecules, or the reaction involves two NO2 molecules proceeding via some elementary step to do the thing. Is sort of what that tells us, the order. And a unimolecular reaction would just involve something decomposing. So that's sort of that there. Last, I suppose next we consider something called the rate determining step, which is the bottleneck of a reaction. It's the slowest step in a mechanism, and when one step is very fast and the other is quite slow, we just assume that very fast step just doesn't happen, and it contributes nothing to the overall speed of the reaction. Um, it would be analogous to saying that, say there was a hill to go to the school, and the time it took for you to go home was the time it took you to go um, from the school to the hill, then to go up the hill, and then to go home. Now, the obvious way to speed up the time it takes for you to go home is to just climb the hill faster. Sure, you could walk faster from the hill to your house, and I'm sure you would get a little bit faster there. But the difference in speed is not quite as noticeable as if you climb the hill faster. Is sort of the idea behind the rate determining step. It generally is the slowest step at a reaction, and if you speed it up, the reaction will be much faster. The differential rate law for the entire reaction can be written generally if the rate determining step is the first step. When you write your differential rate laws, you can just ignore the other stuff here. So here, for example, we can ignore this fast step, and therefore the reaction the rate law for the reaction is just rate equals k times NO2 squared. Since we can assume this step just doesn't happen, it doesn't contribute anything to the rate. The overall rate does not depend on carbon monoxide, since despite that it's a reaction, it's involved only in the second step, and that is much faster, and it therefore doesn't influence the overall rate. Considering the orders are involved, doubling the carbon monoxide reaction would double the rate of step 2, but it would have no measurable effect on the overall rate. Nextly, we talk about a transition state, or an activated complex, which is a complex species found at the potential energy maximum as reactants proceed to form products. It essentially exists at the point of collision. Basically, it's just what's the transition. The transition state is basically the in between the products and the reactants. It's sort of at the highest energy it has the highest potential energy, since it has the most amount of bonds to it, and it's essentially what you have at the point of collision. The thing you have at the point of collision. So this is a transition state here for this particular species, and then you would decompose into that. And then similarly here at this potential energy maximum, you would have this transition state, and then this O would break off to form CO2, and you would get N2O there. When you get a proposed mechanism, it's not possible to determine with 100% certainty that the mechanism is correct. However, you should generally follow these steps. The steps of the mechanism must add up to the overall reaction. The orders in the differential rate laws must be consistent with the basically the orders that you get experimentally must be consistent with the mechanism that you determine the rate law for. And then lastly, if you had proof of this existence, obviously that would be great. So for example, spectroscopic evidence that the intermediate would absorb a specific wavelength for, and say you encounter absorbance of that particular wavelength during the reaction, it would be very strong evidence to propose that intermediate does exist when that reaction occurs. And consider a multi-step reaction here and its energy level diagram. So here we have activated energy complex 1. Here's the activation energy. This is delta H. So step 1, which is the slow step in this particular reaction, because this is nucleophilic substitution. When we do OChem, you'll actually become very familiar with this. But here we have the first step, which I just happen to know is slow, just because I know what that is. And then the second step here is fast. So the first step involves the formation of this cation, this anion, and then you have these three existing, and then you have this OH bonding to this thing here, and you get a bromine. Catalysts, I'm just going to re-mention the definition again, and hopefully after all we've covered, you'll get an appreciation for what the whole definition is. A catalyst is something that provides an alternate mechanism for a reaction by providing a reaction pathway with a reaction pathway with a lower activation energy. So it provides than the original uncatalyzed mechanism. So generally, I suppose that's sort of that there. Now, what if the first step is not the rate determining step? Well, what you assume is that all the fast steps, you assume that the fast steps go to equilibrium, and then you can use that fact. So let's do this worked example here. So here's the overall reaction, and here is the fast and the slow step. Now let's head over to the whiteboard, which is what we call MS Paint, and our overall reaction is A plus B plus C plus A plus B plus C will form compound E, right? And the first step is that A plus B form D, and then D plus C forms E, right? And we are told that this is the slow step. Now, since this is the fast step, what we can assume is that this goes to equilibrium, and we know that Kc equals, let's actually first write out the differential rate law for this elementary step. We know that it is equal to K times D times C to the order of 1. Now, what we know is that from here, we know that Kc is equal to D times A, and then times B. Now, we can rearrange this to get that. Let's rearrange that. We can get that, and these are all to the order of 1. K times A times B. Now, what I forgot to mention is that while this is fine and good, you cannot write rate laws with intermediates. You have to write them in terms of just the reactants that you start with. So we get that K times A times B is equal to the concentration of D. Now we can substitute we can substitute this here, and we get that K times Kc times A times B times C equals rate. However, these are just arbitrary constants that we don't know, so why don't we just collect them and call this, since these are just arbitrary constants, let's combine these two to make another arbitrary constant, which I will just call K for the sake of being lazy, and then we therefore get K times A times B times C. Well, that's off from the convention. However, you just factor these things together to get this K. It would be equivalent to just, if you've done integration, it would just be equivalent to plus C, and then if you do parts, you add another constant, which would be, let's call it D, and then C plus D is just another arbitrary constant that you just call C. It really makes no difference what it is, since it's an arbitrary constant that we can find out later is equal to the rate. And if I check my notes, that should be what we get. We get that, yep, C, K times A times B times C is the overall rate. The overall rate is a function of the reactant species in steps 1 and 2, not just the RDS, as we see here, if the slow step is not the first step. How am I doing for time here? Okay, I could probably cover ozone depletion. And an interesting sort of real world. Now let's take this to the real world, I suppose. Let's look at ozone depletion. And we can see here that the main cause of ozone depletion is the release of chlorofluorocarbons that will, under the presence of UV light, break into form these radicals here. This carbon, chlorine, this radical here, and this radical here. In addition, you also have nitrogen monoxide, which will form this in the atmosphere. Naturally, in the ozone layer, UV light will break down O2 to form these oxygen radicals, and then these radicals will form diatomic oxygen, and this equilibrium is maintained. However, when we introduce outside chlorine radicals, they will react with the oxygen radicals to form these radicals, and then these radicals react with this one to form O2 and Cl, And the overall reaction is this. No, these chlorine radicals react with ozone to decompose it into oxygen, chlorine, and then you will get this chlorine oxide plus this radical here will form this one and this one. This is just something you have to memorize. I have no real way to. In fact, I don't even remember this really. The idea here is that the chlorine radicals will react with the ozone to decompose it into oxygen, diatomic oxygen plus chlorine. This is really bad since ozone absorbs different wavelengths than diatomic oxygen, and it just so happens that those wavelengths are really high energy from the sun, and they essentially shield us from that. And if that radiation hits us, it can cause things like skin sunburns and whatever, and all that stuff. And then with nitrogen monoxide, you have a similar sort of mechanism here that I'm not going to go over, but it's the similar idea with the chlorine radicals. And with that, thank you very much.